All right. Good morning, good afternoon, good evening, everybody. My name is Gerald Pasquale, and this is kind of a change of pace from our previous webinars in which I would just be the MC here. Today, we are going to be performing, or giving a presentation rather, on an interesting research project that we recently presented over at the Physics and Chemistry of Surfaces and Interfaces conference in New Mexico, actually the other week. And this was going to be based on graphene Moira pattern ultra-high resolution atomic force microscopy. So let me go ahead and share my screen here. And what you guys should be seeing is a set of slides, or rather the title slide, for the presentation I gave at that particular ABS conference. And we're going to be going over the results of this particular research project. Let me see here. It's a little paused for a minute. Let me go ahead and get that back so it's showing to everyone there again. And we're going to be talking about the technology that went into characterizing a graphene sample that exhibited a superlattice Moira fringe, or Moira pattern, on the surface of the sample. And I'd like to begin with first just going over exactly what a Moira pattern is. Maybe there's some folks here who aren't familiar with what that particular surface phenomenon is. And then we'll be going over the technologies that went into it, specifically the atomic force microscopy system and the operation software that allowed us to characterize the topography of the graphene Moira pattern, basically with as little human interaction or human input as possible. We used an operation software that self-optimizes the scan parameters, which basically posits that we could have someone with little to no AFM training creating such images right from the get-go, maybe from only a couple hours of training on the software. They'll be able to just produce this right from the get-go. So let me go ahead and go into presentation mode here. I see a couple names here that are not familiar. Looks like you guys are new. So you might have noticed that if you were trying to go ahead and ask a question right from the get-go, that the mics are in listen-only mode. They're disabled. That's by design. That's part of the software here for the webinar. And let me see here. Full screen mode looks like it's cutting off a little bit of the slide, so let me exit that for a minute. And what's going to happen is if you have any questions at all, go ahead and type them in using the questions module that's loaded up in your control panel when you joined up for the session here. And what we'll be doing is, at the conclusion of the short talk, maybe 15, 20 minutes or so, I'll be bringing in a member of the technical staff here at Park Systems in Santa Clara. Any questions that I can't answer that are beyond the scope of my knowledge, I'll go ahead and bring someone in, and we'll have technical answers for you. And then, of course, if there's anything that comes up afterwards, remember these webinars are all recorded. They're all posted on parkafm.com and on our YouTube channel, youtube.com/user/parknano. And they're available for viewing for all of posterity. Okay. So let's see here. There's going to be a couple of animations here on the screen, and I'm not sure how the refresh rate is going to show up on GoToWebinar. If portions of it are cut off, just go ahead and let me know in the questions module. I'll try to explain visually what's happening here. But first, I wanted to start off with, what is a Moira pattern? So a Moira pattern is a large-scale interference pattern when two monolayers, here in this case, two sets of horizontal lines, are moved on top of one another and create a secondary visual pattern wherever they overlap. So one common place that I've seen this happen in my childhood is actually on screen doors. So if you live down in portions of the country that are hot, usually you have a screen door that'll allow air circulation to pass through a wire frame. And sometimes you'll even have two screen doors overlapping on top of one another. And as you move, as your visual perspective changes, maybe you're walking down the room. As you look at those screen doors overlapping one another, you'll notice that there is a visual pattern that occurs wherever they overlap that is only visually evident. It's not actually there. So this is what this animation is trying to simulate. And this is essentially the type of feature that we're trying to characterize on our sample surface. We have a monolayer of graphene that's been grown on top of hexagonal boron nitride. Those are our two layers. And as the graphene is offset by rotation on top of the HBN, it produces, again, a visually evident pattern, a Moira fringe, where those two layers overlap. So here are some other examples of where you'll see Moira patterns. Here's another good one from an office. This is a wire waste basket. So if you've ever passed one of these things, as you move your position around the waste basket, the wire framing on the side of the basket closer to you overlaps with the wire framing on the basket side that's farther away from you, and it produces this interference pattern again. At a park of some kind, wire link or wire chain fences, same exact thing. The holes in the fence have a specific periodicity. The constants between each of the wires in the frame are of a constant length, right? And as you move past the chain fence, there's an interference pattern that results there. You might also see it on your laptop screen. Some screens' constructions also display a Moira pattern depending on what angle you view the screen from. And then sometimes when you're shooting someone on a video camera, if they're wearing a shirt that has a lot of stripes or a lot of bars on it, like this person's shirt right here, you might start to see that on the footage that you've recorded. Okay, so graphene, this will be really quick because it's a very popular topic for research these days, but the particular sample, again, that we were using here is focused on graphene, and graphene, as you can see, has a lot of different potential applications, whether it be through the development of new sensors, the development of transparent electrodes, different kinds of wiring materials. In this particular case, the sample that we were looking at was created because I believe they were trying to create a new type of high-speed transistor. And so on the bottom here, on the bottom figure, you'll see the basic outline of the sample that we were looking at. At the very bottom of the sample, everything was placed on oxidized silicon. And then we had hexagonal boron nitride, HBN, and we used that as a substrate for growing graphene on top of it. And this particular figure shows how this potential graphene HBN device would be used as a spin device, as a transistor device here. You'll see that it has a source and drain and also a voltage gate here. So this is a very simple diagram for a graphene HBN device. And because the fact that we're trying to develop next generation transistor devices, we need to have a substrate that promotes higher mobility of electrons across its surface. If you're trying to build a high-speed network, you don't want to use broken rails. You're going to want to use something like graphene that has very well documented conductivity. You want to be using more modernized rails. You want to be able to build something that can move much faster than previously existing materials. You want to build a bullet train. So here are the different production methods of graphene and HBN devices. Again, a little bit more background onto the sample that we're looking at, just for some perspective here. So the very most basic way of growing graphene is direct transfer. It's okay as a beginning method of growing graphene. However, it's very low yield. Can't really control the orientation of the graphene that is produced. And as a result, it's a little unreliable in terms of its electrical properties. You'll still get some usable graphene, but this is not the optimum choice for this particular application. Next, we have metal catalytic CVD. So this kind of vapor deposition, it's essentially the same as growing graphene in a direct transfer, the previous method. There is some complexity in the transfer process. You'll see here in the figure below the growth front of the graphene. It's definitely a little. It's definitely not under total control, as you can see here. There's a lot of jagged edges as the graphene is being grown on top of the copper. But what we're looking at here with the HBN device is we're getting rid of the copper in this case. We're not going to be using a metal catalyst. We're going to be using, again, boron nitride, hexagonal boron nitride. And at defects on the boron nitride, this is where we see graphene nucleation. And this is where we start to see a uniform monolayer graphene being grown at these substrate defect sites. And you'll notice that we specified hexagonal boron nitride because we wanted to have a similar constant shape and pattern to to graphene, which is also hexagonal in nature. So in this case, this is where we have a lattice constant in one layer being slightly different than the lattice constant of the layer below it. So we're looking at graphene of having a lattice constant, in this case, of 2.46 angstroms. HBN is going to be at around 2.5. And that translates to a mismatch of around 2%. So here is, in the lower right corner, another example of the superlattice Moira pattern that's being created that we're going to be observing with AFM on a sample that contains two layers that have slightly offset hexagonal lattice constants. The superlattice constant is going to be the portion of the sample in the middle that has a honeycomb type shape. You'll notice that if you focus a little bit closely here, you'll start to see a huge, larger hexagonal shapes with areas of high particle regularity or high regularity, vertical regularity between the graphene and the HBN, forming the cells of the honeycomb. This is, by regularity, I mean the alignment of the graphene atoms on top of the HBN atoms they're more in vertical alignment than they are in the borders of the honeycomb cells, the lines that distinguish the different hexagons in the superlattice pattern. They're more vertically aligned with one another, so it appears that there's a space there, and that's the superlattice constant. And then the areas where the graphene and the HBN are not as well vertically aligned with one another, those are the areas that look thicker, that appear thicker in the superlattice pattern. Again, the borders between the hexagonal combs, or hexagonal cells in this honeycomb pattern. And here is an image of what it looks like inside of one of these superlattice constants, inside one of these superlattice honeycomb cells. So you'll notice that towards the middle of the image, there is, again, regularity, perfect regularity in some of the particles of the HBN. Let's call blue the HBN and red the graphene. Or actually, in this case, since blue is on top of red in the middle, let's call blue graphene, let's call red the HBN. So towards the middle, where there's more and more blue, where it appears that there's an opening in this pattern, we see that the particles have a high degree of uniformity, vertical uniformity. They're right on top of one another. But because of the lattice mismatch in their respective layers, as you move towards the edges of the picture, you'll start to see that the particles are not overlapped anymore. And this causes this creates rather the appearance of the borders of the honeycomb cells in the superlattice. Okay, so why did we pick AFM? Well, aside from the fact that Park Systems is, we specialize in AFM, we noticed that HBN is an insulating substrate, so we really couldn't use STM in this case. we had to characterize it with a non-conducting technique. So we just use non-contact mode AFM here. The other thing that we had to keep in mind was tip sharpness is critical here, because tip sharpness, the sharper your tip, the higher resolution that you'll be able to resolve, the smaller features you'll be able to resolve in your final image. The trade-off being, though, is if you run it in contact mode or tapping mode AFM, you tend to wear down your super sharp tips much quicker. And the cost, as many of you who work with AFM already know, the cost for super sharp tips, especially in volume, can definitely hinder research projects with limited funding. So that's why we definitely wanted to use non-contact mode AFM in this case, just to mitigate the tip wear and to preserve the tip sharpness for showing that the characterization of the patterns on this, or the characterization of the features on the superlattice pattern could be something that could be done repeatably, and again, without advanced tip wear. And we also wanted to keep resolution as well. Parameter optimization was the third factor that led us into characterizing this with AFM. I briefly spoke about this a little bit earlier in that AFM has traditionally been a technique that has been very dependent on the skill set of the operator. There is a notion that AFM is really something for that requires a specialized trainee in order to acquire really good images that are required for publishing out in journals and in different journals. Yeah, different journals. So actually, not too long ago, we've developed a software that helps mitigate the impact of needing a guru, an AFM guru of sorts, and helps reduce the learning curve for high-quality, high-resolution, repeatable AFM imaging. And this is a self-optimizing scan control, scan parameter software. So again, we're trying to remove the necessity of having someone who is well-versed in AFM imaging already. We're trying to remove that from the equation, and we're trying to get people who are legitimately interested in AFM imaging but don't have the experience to do so, creating great work right from the get-go. So again, the purpose of this was to test the resolution limit and repeatability of imaging via non-contact mode atomic force microscopy. Again, the monolayer graphene here was grown on an underlay of HBN. And before we go to the data, again, the Moira pattern was created when the graphene layer was offset by rotation on top of the HBN. And here is that diagram again showing the superlattice constant, the honeycomb pattern of the superlattice Moira fringe. All right, now the results. So we did a series of 4 scans consecutively, one right after another. The first one was an initial survey scan. We're looking here in the upper left corner, a scan that was about half micron by half micron. And if you look really closely, you start to see that there is some kind of uniform pattern occurring all across the image. And for some third-party observers, particularly those at the PCSI conference, they were wondering, okay, that general haze that's occurring over the pattern, is that noise? Or is that something that's actually real? So we asked ourselves the same thing. And again, we blew up the magnification here. This time we're looking at a quarter by quarter micron. And you'll notice that here in the lower left corner, we looked at a feature of high contrast that was in originally the upper left corner of the previous scan. But as we can see here, that overlay that's occurring over the entire scan, it's not noise. There is definitely a set pattern occurring with a uniform regularity all across the surface of the sample in a series of areas of darker contrast that look like holes. We blew up the magnification again. And this time we're looking at 125 by 125 nanometers. And by the time that we get to this level of magnification, we see that the superlattice constants, or the areas here in this image of darker contrast, they're not occurring randomly. You'll see that they're staggered. Yes, they're definitely staggered, but they're occurring, again, at regular intervals and at more or less the same diameter as one another. One superlattice constant isn't bigger than the other. It's definitely something that's uniform, that's repeating. Now, this is the last scan in the series that we did for this graphene HBN sample. This was done at 60 by 60 nanometers, and there were a couple of definite observations here of note that we definitely wanted to point out. One of which was pretty surprising. It was unexpected. So first, we wanted to measure the superlattice constants, the areas of darker contrast at their widest. So we took a look at their width in the horizontal direction. And we found that they were just about 50 nanometers in diameter at their widest. And that was typical of every single lattice constant that we measured here at the 60 by 60 nanometer scan. And that was something that we did expect, because we saw the superlattice constants appearing as far back as the 500 by 500 nanometer scan, the first one that we looked at in the series. But what was surprising was that as we moved in at higher and higher magnification, so the surface of the sample, we detected a secondary Moira pattern. Here, I'm highlighting them for you, just so it's a little bit easier to see. But you'll probably already take note of it in other portions of the image. But running along these yellow dotted lines, we saw striations. We saw stripes. And stripes that, again, had a degree of uniformity to them. They occurred from the upper right corner to the lower bottom corner of the image in this particular scan orientation. And they were happening at 4 to 5 nanometers apart. This is something that, again, we didn't expect to find. Neither did our collaborators who provided the sample over at Stanford University. This is something that they weren't expecting to find either. And in fact, their work has been replicated and published in Nature Communications Journal. And I can give the reference for that if anyone's interested. But this just goes to show that there is still space for scanning probe microscopy to work for characterizing features at this small of a scale. Really, the only thing that we're limited by, interestingly enough, is going to be the geometry of the probe. So again, all of these scans that you've seen in this series, all 4 of them, they were done with one single AFM probe, all in non-contact mode. And the tip radius of curvature on the probe that we selected was, again, nominally around 5 nanometers. So we're hypothesizing here as a group here in Park, US, that if potentially someone were to come out with an even sharper probe, let's say tip radius curvature of 3 nanometers, or even below, let's just throw it out there, we definitely are confident in saying that we would be able to resolve even smaller features of topography and maybe of other characteristics of the sample as well in non-contact mode at that tip radius of curvature. So if there's something here on this surface that's only 3 nanometers, maybe there's a tertiary Moira pattern that will appear only when you have a sharper tip, we're confident that really this is the main limiting factor. Give us a sharper tip and we'll be able to resolve something that's even smaller than what we see here. As to the purpose of these striations, or if they have any special characteristics, we didn't really push the investigation that far. We did do this at a series of different scan rates, so it's probably not an artifact there. And we also did this scan with the sample oriented differently on the stage, so it's not a product of the sample being oriented in a certain direction. But it just goes to show you again, SPM, particularly AFM, definitely has more and more applications that are just limited by probe geometry at this point. Another thing that I wanted to point out that I mentioned earlier again was that while the initial scans of this sample were done with an operator controlling the AFM manually, optimizing the parameter using their own personal experience, we were able to replicate these same results with our AFM running with autonomous control, with the software controlling the AFM. So again, if this is something of interest to people in research groups who have to train a lot of new users, people who haven't really used AFM before, they can simply rely on the tool and the software to produce these images for them, and they'd be able to get this same kind of research done on their own. Okay, so this is basically my last slide, and this is, again, kind of a shorter session than we normally run here for our webinar series. And I just wanted to conclude again by reiterating that we're only limited by probe tip geometry at this point, and non-contact mode AFM can definitely provide high-resolution, repeatable data when observing nanoscale phenomenon, such as the superlattice Moira fringe pattern. Okay, so with that, I am going to go ahead and open it up to questions. And again, I'm not the most technical person here, but if there is a question that I cannot answer, I'll go ahead and bring someone in from our technical staff, and we'll try to get as many questions as answered as possible. So let me go ahead and give you guys maybe 30, 60 seconds to type in questions, and I'll go ahead and review what's already in queue. But with that, thank you very much. Let's see the questions here. Oh, okay. So looks like we do have one question here. And also, thank you, yeah, thank you to the audience who said, sent in their thanks here. Okay, whoa, looks like there's a lot of questions. Okay, let me take a look here, guys. One moment. Okay, so as I expected, there's a lot of feedback here, and some of this I may have answered already. So I'm going to start with our first question here. Let me know if my reply is not satisfactory, if it's missing a couple of details that you're looking for, guys. And then I'll bring in someone from our applications lab really quickly, and maybe they'll have some more technical feedback. So our first question here is, how can we say that the secondary Moira pattern is not an artifact? Okay, well, in this case, I wanted to, let me go ahead and go back to that slide. Okay, here we go. The 60 by 60 nanometer scan. There were a couple of factors here that helped us at least believe that the secondary Moira pattern was not an artifact of scanning. First is we were able to produce this type of observation of the striations, of the stripes, at different scan speeds. I think we tested it at like 5 to 10 hertz. Those are the two most common speeds that we usually scan at. And we were seeing the secondary Moira pattern occurring at both of those scan speeds. In addition to this, the other thing that led us to believe that this is probably not an AFM scan artifact is that this work that I just presented here from the office in Santa Clara from Park Systems, it's actually a replication of work that was done by the Goldhaber-Gordon group at Stanford University. They went ahead and published, I think last year, a paper in a Nature Communications journal. I'm not sure if it's the Nature, but It could have been like Nature Energy or another one of Nature's different magazines. But they've gone ahead and published this work there where they have observed the striations in pretty much the same exact sample that we looked at here. And actually, I think that's recommended reading probably. So before I close the webinar here, I'm going to throw the citation, the Nature citation for that article, into the chat because they definitely went through and saw the striations under a much larger different set of conditions than we did here for this particular study. So we're definitely going by what Stanford and what Nature felt was good enough to publish in their publication. Okay. Is it possible to get images with higher acquisition time? And there's a follow-up to that. I mean, let's see here. I see from the last slide that you have used high-speed AFM. Okay, so what's being talked about here, I guess, is the last slide in the presentation. Let me go back to that. So what's happening on the screen here, and I think I failed to mention this while the animation was originally playing, was that this is actually a look at the software that's being used to self-optimize automatically the scan parameters and the different features different settings rather, that go into the scan of the HBN graphene sample. By higher acquisition time, this is a follow-up question to the question answer. Do you mean like setting a lower scan rate? Is that what you're asking? Okay, yes. So the answer to the question is yes, you can go as slow or as fast as you want, even when using this software. This is called the auto mode of Park Smart Scan. And essentially what it does is it allows the user to trade off between scan speed and scan quality. So there's a slider that helps you tell the software, okay, software, I want you to be biased more towards accomplishing a slower scan rather than a faster scan. So if you wanted to go as slow as like 1 hertz, you could tell it, okay, go as slow as possible, get as fine detail as much as possible from the scan as you can, versus the other end of the spectrum, which is, you know what, I need these scans really fast. Go ahead and just blitz through the entire sample range that I've specified and collect what you can from going as fast as you can. So there is a way to tell the software, hey, go ahead and go as slow as you wanted to. And if the auto mode, in this case, if the slowest speed that it automatically determines for itself is still not good enough for you, the good thing is we still have a manual mode in this scan control software. So if you wanted to dictate a completely user-defined scan rate, you still can do that. Okay, let's see here. Could you show some images for scanning Kelvin probe microscopy for graphene? Well, actually, that might be a question that I can follow up after the webinar. Let me go ahead and send my my email address to you guys, because right now I actually don't have anything else prepared besides the non-contact topography data for this graphene HBN sample. So in this case, Fatima, go ahead and email me, or anyone else here, if you have any questions. Email me at gerald@parkafm.com. What I'll do is, if we don't have any SKPM data for graphene, if for some reason I don't have access to that, we may potentially have them at our different offices, like our World HQ in Korea. I'll go ahead and confer with the technical staff to see if that's something we can dig up. Okay, any other questions? Okay, thank you, Fatima. So before I part with you guys today, I did promise to go ahead and get that citation for you guys. Okay, let me go ahead and see if I can pull it up. Give me 1 second. And while I'm pulling up that Nature Communications Journal citation for that Stanford group that looked at the same exact sample, what I'm going to do is I also want to note that, again, if you go to parkafm.com, what you'll do is under the Nano Academy section, you're going to have a repository for all the different webinars that we've done in the past. And if you wanted to share it with a colleague or with a student, you could definitely have them look at that recording, and they'll be able to watch that. For this particular webinar, I won't be able to share the slides, just because we have a couple of things in here, like, for example, the user interface for our operation software in here. But we will be able to pretty much show the rest of the webinar series that we've done in the past. So no matter what background that you're from, whether it be for energy research or materials development or even biomedical applications, we have a webinar for you. So feel free to check it out. Again, it's a Nano Academy at parkafm.com.